So at the end of the last video, we talked a bit about what your body might do in terms of central control mechanisms in response to low blood pressure. And we said that if your blood pressure drops, you'll detect that with baroreceptors, for instance, your carotid sinus or aortic sinus. And you might crank out some epinephrine. Your kidneys will probably produce some erythropoietin, which will be a long-term response of making more red blood cells. It will also produce renin, which will cause your body to produce antidiuretic hormone, which will bring back more fluid, aldosterone, which will bring back more sodium and therefore fluid and cause you to become thirsty. And this will also cause you to crank out the production of angiotensin, which will cause constriction of your blood vessels, and all of these things will raise your blood pressure, some more quickly, some over a longer period of time, and bring you back to normal. Well, what happens then if your blood pressure is too high? Well, you'll have a similar response, but with a few different chemicals. Your baroreceptors will detect this as well, and you will crank out natriuretic peptides. Now, if you remember from chapter 16, these are the opposite of aldosterone. Aldosterone is your salt-retaining hormone. Natriuretic peptides are your salt or sodium getting rid of hormones, for lack of a better opposite to retaining. And you have one that's produced by your heart called atrial natriuretic peptide, and one that's produced by your brain that is appropriately called brain natriuretic peptide. And these cause you to get rid of sodium, and water follows the sodium, and that drops your blood fluid and blood volume, and therefore your blood pressure. So if your blood pressure goes up, your cardiac muscle cells, for instance, will detect that and release natriuretic peptides, will cause your kidneys to get rid of more sodium, and more fluid will also follow, and that will also reduce your thirst and counteract or inhibit the action of all those hormones that we talked about just previously, and that will cause your blood pressure and blood volume to drop. Now, in addition to baroreceptors, which detect pressure, we also have chemoreceptors of various sorts that detect chemical levels. They could detect, for instance, carbon dioxide, and that's important because if you have not been breathing in a while, or if you're producing a lot of energy, you're going to produce a lot of CO2 as a waste. It can also detect oxygen, pretty important, and pH, which is sort of a proxy for these other two, because the more CO2 you have, the more acidic your blood is going to be, the lower the pH is going to be. And that generally ties in with low oxygen levels too. So where are these receptors? Well, you've got several of them, but you've got some big ones in your carotid bodies, which are also at the base of your internal carotid artery, and your aortic bodies, which are also in your aorta, right next to the carotid and aortic sinuses that have those baroreceptors. You also have chemoreceptors in your medulla oblongata, which is important for regulating your cardiovascular system. So let's say that you are exercising a lot, right? Or you're not breathing very well. Maybe you're choking or something. I don't know. For whatever reason, your oxygen levels are dropping and your CO2 levels are building up, right? This is also going to cause your pH to drop, right? You're going to become more acidic because carbon dioxide, when it comes in contact with water, which your body is filled with, makes carbonic acid. So your pH drops. Well, you're going to detect that in these carotid bodies and aortic bodies, and also in your medulla oblongata, and that is going to stimulate you to do a couple of things. First of all, breathe more. Breathing more is going to bring in more oxygen, get rid of more CO2, and that will then fix your pH. It's also going to cause you to crank up your heart rate, because if your blood oxygen level is low, well, then you better get more blood per minute to all of your organs so that they can maintain their energy production, right? If I'm trying to bring you food to survive, right, and I'm bringing you truckloads, I either have to have full trucks, or if I downsize my car, right, I can carry less stuff in the car, just like less oxygen in your blood, well, then I'm going to have to make more trips more quickly. And when that happens, hopefully we're going to bring you back to normal. And you can do a lot of adjusting of your cardiovascular system just by adjusting your cardiac output, which again is primarily going to have to do with your heart rate. So when you are at rest, so right now, you're sitting back, you're watching this video, your cardiac output is probably about 5,800 milliliters or 5.8 liters per minute. And of that, 750 is going to your brain, 1,100 to your kidneys to filter out blood, 1,400 to your viscera to absorb nutrients from maybe the food that you just had, about 1,200 to your muscles. I don't need to know these exact numbers, but I wanted you to get a relative idea. But what happens if you start exercising? Well, during light exercise, your blood vessels are going to require increased capillary blood flow. You're going to get increased venous return because your skeletal muscle pumps are working, and that's going to increase your stroke volume. Your heart rate's probably going to crank up a little bit, and your cardiac output is going to increase from about 5,800 to about 9,500. Again, largely due to this extra venous return because your skeletal muscle pumps and your respiratory pump are pushing that venous blood back effectively. And during heavy exercise, you're going to go up even further. Maybe 17.5 liters of blood per minute are going to be coming out of your heart, and you're going to be changing where you're sending this blood, right? You're going to be sending a lot more of it to your skeletal muscles to power those muscles as you're exercising, to your skin to promote heat loss, right? To not only to produce sweat, but also to cool off that blood near the surface of your body. And you're going to reduce blood flow to your viscera, your intestines, etc., because you're not going to be digesting and absorbing food. And this figure is a great way to visualize this, right? At rest, I know I'm blocking some of this, but this is the figure that we looked at before. Notice what beefs up as you move forward toward heavy exercise. First of all, your total cardiac output is going to be much larger, right? Essentially triple, sometimes more than triple for heavy exercise. You're going to be sending less blood to your kidneys. So even though we're making 3 times as much blood come out of your heart at any given minute, less absolute blood is going to your kidneys, less is going to your viscera, more is going to your skin, and way more is going to your skeletal muscles, right? Because this is where we need the energy. And about the same is going to your brain at any given time. Now, these are all averages, right? If you are an athlete, right, maybe an Olympic level athlete, right, you're really in shape, you're going to have probably more hemoglobin and more red blood cells. And so you don't need to crank up your heart rate as much to walk up the street, right? Whereas someone who's maybe not an Olympic athlete may start walking and have to crank up their cardiac output. And that also means that at rest, their resting heart rate is going to be much, much lower. As low as 32, although that is really, really low. Again, typically below 60 is low. And your maximal cardiac output could be way higher than non-athletes, right? Because your heart is better at its peak, cranking out more blood. Well, what happens if rather than a little increase or decrease in blood pressure, or a little increase or decrease in need for blood, so cardiac output in response, instead of that you have blood loss, like dramatic blood loss? Well, you kind of have immediate and long-term issues. Your immediate problem is maintaining your blood pressure and blood flow to your periphery. Long-term, you need to restore your blood volume, right? You need to bring your blood volume back up to normal. But in the meantime, you can cope with blood losses equal to about 30% of your total blood volume, right? Now, you're not going to be running any marathons, but you can survive. Now, short-term, you're going to cause some very quick vasoconstriction, right? And that's going to, again, reduce the volume. So if you've reduced the amount of blood, you have to reduce the volume to maintain the same pressure. You're also going to crank up the heart rate. And this is, generally sympathetic activity and epinephrine, maybe to 180, 200 beats per minute. Again, just to keep your pressure up, because you have to be getting blood to your organs so that you can keep that tissue alive. Kind of medium and long term, you're going to be cranking out aldosterone and ADH so that you can retain sodium and fluid as much as possible by the kidneys. You do not want to waste any body fluid by urinating more than you have to, absorbing as much water as you possibly can through your digestive tract, and cranking out for the longer term erythropoietin to replace those lost blood cells. So again, you're going to crank up your heart rate, you're going to vasoconstrict your peripheral blood vessels, you're going to maintain blood volume and produce more blood cells and increase blood volume if you can, and hopefully maintain as much blood volume and blood pressure as you possibly can. Now, if you can't keep up, if your blood pressure is so low, so hypertension is high blood pressure, hypotension is low blood pressure, that you cannot adequately perfuse your organs, this could be local. So this acute cardiovascular shock could be local or broad, and we call that circulatory shock. Right? Shock is when your blood loss is greater than 35% and you're not able to keep up to get oxygen to your organs. Now, this can either be due to hemorrhaging, so severe bleeding, or heart attack, right? If you're not able to pump blood through, then you're not going to be getting oxygen and blood to your tissues. Now let's back up to the beginning. Your blood vessels had to come from somewhere, right? And the process of building your blood vessels involves two processes. The first one is called vasculogenesis. Genesis means the production of, vasculo means vessels. This all makes sense. And this happens from stem cells that are called hemangioblasts. And hemangioblasts are actually the first precursor cells of your cardiovascular system. This is occurring in your yolk sac. Yes, you have a yolk sac when you are very, very early, right, like a week in. And hemangioblasts, heme means blood, angio means vessels. They will create a couple of kinds of stem cells. One is hematopoietic stem cells, which will give rise to all of your blood cells, and we've talked about that. But in addition to that, hemangioblasts will also give rise to angioblasts, which produce your blood vessels. And so this very first production of blood vessels that happens when you are, a week, 2 weeks, 3 weeks old, as an embryo in your mother's uterus, is called vasculogenesis. When you're producing this primitive vessel network. And here you can see these hemangioblasts and these hematopoietic stem cells. Again, the hemangioblasts will make the hematopoietic stem cells, and angioblasts that will produce these blood vessels. Most of this happening in your yolk sac when you are your parents probably haven't even noticed you're there. But during the rest of embryonic and fetal development, and then also as an adult, right, you still are producing new blood vessels. From those older ones. You're adding on to pre-existing vessels. And this is called angiogenesis, which also means vessel production. We just use a different word. So vasculogenesis for the initial production, angiogenesis for this later production where we're adding on to what we had before. And again, this happens even when you are still an embryo. We're adding on to these initial vessels to get more extensive networks. Now, as a review, as an adult, you have two main circuits of blood flow. You have a pulmonary circulation or circuit and a systemic circuit. Your pulmonary circuit takes blood from your heart to your lungs, from the right side of your heart to your lungs and back. And then your systemic circulation takes blood from the left side of your heart, oxygenated blood, away to the system, right, to all of your organs and tissues, and then back to the right side of your heart. And in the next video, we're going to talk in a lot of specifics about a lot of the arteries and veins that you find in those systems.